in another parenthesis. Okay, so if you don't mind, I'll start doing 216. And I should perhaps start by apologizing because the problem does not quite fit into the framework that we have in the course so far. And the problem is that the random variables we looked at so far are taking values in the real numbers. Now later, when we start looking at limits of sequences, it may be that these limits are infinite. And then it's more convenient to look at the random variables which can take values in the extended real numbers, where you add minus infinity and infinity. So if you take r bar to be r plus minus infinity and infinity, you can still define a random variable in the same way. So x, a random variable in this extended sense is a function from omega into r bar such that the sets of all omegas such that x of omega is, let's say, less than alpha is in the sigma algebra. It's exactly the same definition, you just allow values plus and minus infinity in addition. And of course, infinity is larger than all the real numbers, minus infinity is less than all real numbers, but you still use the same definition. I mean, for this problem to make totally sense, you really have to look at random variables in this extended sense. You may wonder, what does value plus infinity really contribute? But it turns out that in the problems we should be looking at, the random variables will take the values plus and minus infinity with probability 0. They just sort of appear naturally, but they are so rare that they don't really point to them. So let's look at the problem. The first problem, we have a sequence of random variables, xn, and we are looking at the supremum of those. So introducing a new random variable, x of omega, which is the supremum. For each omega, it's the supremum of the set xn of omega, n is in natural numbers. So all of these, of course, if you fix omega, all of these are real numbers. So I have a lot of real numbers here. And I'm looking at the supremum, least upper bound of these real numbers. So in this case, that might be here perhaps. So this would be x of omega. Now it could, of course, happen that these numbers get arbitrarily large, and then we just let the supremum be plus infinity. That's why I need plus infinity here. It could happen that this is an unbounded set, and then supremum in the usual sense is not defined, but we just take plus infinity to be the supremum. And what I need to prove is that if these x and omegas are random variables, then this x is also a random variable. So how do I prove that? Well, these different descriptions of random variables still work. I mean, this may be the basic definition, but we know that we can get away with unstrict inequality here, or that we can take the inequalities in the opposite direction. And this is one of the situations where it's good to have these different formulations to play with, because it's much easier to prove that this is a random variable using the right variant of these than using the wrong one. So what I'm going to look at is this set. I'm just going to look at the set of all omegas such that x of omega is strictly larger than x. If I can prove that that is measurable and that is in the sigma algebra, then this is a random variable. But this isn't so bad, because how can x of omega be strictly larger than x? Well, the only way the least upper bound can be strictly larger than x is by at least one of these x and omegas being strictly larger than x. I mean, if they're all less than x, there's no way the supremum can be strictly larger. So it suffices here that there's one of these x and omegas which is larger than x. And how can I express that at least one of these x and omegas is larger than x? Well, I can take the union here. And go from 1 to infinity. So if I can prove this equality, I will be in business because these guys are in A, and A is the sigma algebra, so A is closed under this countable union. So I just have to prove that this is correct. So why is this correct? Well, if omega is in here, then x of omega is strictly larger than x. For this to be happen, there must be an n such that x and omega is strictly larger than x. So omega has to be in one of these guys, but then it's in the unit. So everything that is in here is in here. On the other hand, if omega is in here, then there is at least one n such that x and omega is larger than x. But then, of course, the supremum will also be larger than x. So everything that is on this side is also larger. So it wasn't so bad. What about the infimum? If you know that y is the infimum, the greatest lower bound, well, you use the same trick, but you use a different description here. What you now look at is that the set where y omega is strictly less than x. Because in order for the infimum to be strictly less than x, there must be one xn that is less than x. So this turns out to be the union of all omega such that xn of omega is less than x. There has to be at least one x which is less than x, and that is what this union gives you. So it looks sort of tricky because infant soup are sort of complicated objects, but if you pick the right definition, it's not so bad. So in part B, we are supposed to look at lim-inf and lim-sup. Are you all totally familiar with lim-inf and lim-sup?
No.
No. Okay. So what is lim-inf? Let us start with lim-sup here. So let us imagine it this way. So we have a sequence. So this is n going in this direction, and the xn going in this direction. Xn is just a sequence of numbers. So if I plotted them, they would be dots, but I'll just draw them as a continuous line instead. So this sequence will look something like this. I don't want that. So think of this as your happiness curve from day to day, how happy you are. Okay? And let's go in at, so this is day k, and let us look at the supremum of xn for all n larger than k. So what is that? That is the happiest day in the rest of your life. I mean, if you start at k, this is the happiest day in the rest of your life. So this will be this guy here, I suppose. This, make it a little bit bigger. Like this. So it's this guy. So let us give that a name. Let us say that is yk. So yk is the largest happiness you will ever experience beyond day k. Okay. So what does yk look like? Well, you start at the beginning here. This is the happiest day in the rest of your life here. So you're up here. This is the yk curve. I mean, this is the happiest day in the rest of your life from then on. Then it goes downhill here. I mean, this is the happiest day for the rest of your life until you hit here like this. Then you go a little bit downhill, and this is the happiest day of the rest of your life, and so on. So this is the YK curve. I mean, it's just measuring the happiest day of the rest of your life. Now, what is depressing with this curve is that the happiest day of the rest of your life is going down. I mean, once you're past the happiest day of your life, I mean, you go down. Once you're past the next happiest day of the rest of your life, you go down. So this YK is a decreasing, sequence. And I can take the limit of that decreasing sequence. I mean, it always have, if you count minus infinity as a limit, it will always have a limit. So I can take the sequence of this one. So the limit as k goes to infinity of yk, that is by definition what is called the lim sup of the original sequence xn. So it's sort of how far down the happiest day of the rest of your life ever gets. And the limit will exist because it's a decreasing sequence. I mean, it could be minus infinity, but it will exist in that sense. I can also formulate this in another way, because since this is going down, instead of taking, you probably can't see this, huh? So I'll put it up here. So I take the limit of the y case, that is what I call lim sup of the original sequence xn. But of course, since yk is decreasing, instead of taking the limit, I can just take the inf because it goes down and down and down, and the inf is the same as the limit. So I can also take this as the infimum of final k. So there are two ways of expressing this lim sup. I mean, I can take the limit of the YOK, and where I can take the infimum of the YOK. But if I then put in what YOK really is, this is the infimum, and YOK was really the supremum of the xn's. So this is the supremum of the xn for n larger than k. So you can really express lim sup in this way as the supremum of n larger than k, and then the infimum of all the k's. And we are asked here to show that lim sup, if I have a sequence of random variables and I take the lim inf of every path of every x omega, I get a new random variable. So let's see if we can prove that. So what I'm looking at now is that x of omega is lim sup of the original sequence xn. So I want to prove that this one is a random variable. Well, look at it. What does it say? So this is omega here. So let's look at it. This is the infimum over all k, I said here, and the supremum over all n larger than k, xn of omega. Now, by the first part of the argument, this is just the supremum over a lot of random variables from k onwards. So this is what I can call capital yk of omega. This one is measurable because all of these guys are measurable, and we proved that if we took a sup over measurable guys, then we got something that was measurable. So this one is measurable. But now in the next step, I'm taking the inf over all these guys. I proved that all these guys are measurable, and I proved in the previous argument that if I take the inf over a lot of measurable guys, the result is measurable. So just by repeating the two parts in problem A, I get this part. And why is this interesting? Why does anybody care about lim-inf and lim-sups? Well, the main reason perhaps is that they are a way to get into the limit, because what does it mean that the limit of a sequence equals alpha? Well, that is actually equivalent to lim-sup xn and lim-inf xn, both being alpha. So a sequence converges if the lim-sup and the lim-inf coincide, and the limit of the random variable is then the common value of these two guys. So this means that when you have a limit, the limit is measurable because it's equal to the lim-sup, or if you want the limit. So this means that if you have a sequence of random variables and they happen to converge, it's sufficient that they converge for almost all omega, then the result is actually measurable because it's equal to lim-sup and lim-inf, and we prove that lim-inf and lim-sup are measurable. So this is a way of proving that if you have a convergent sequence of random variables, the limit is actually convergent. And since we shall be studying limit problems, I mean laws of large numbers and the central limit theorem, which is actually about limits of random variables, this is sort of the basic stepping stone. We shall do most of this over again. I mean, if you didn't get it this time, you may get it the second time. Okay. So that is 216. Is that reasonably okay?
Isn't there a part C?
I can't remember. I think that was basically what I said about.
Okay, yeah.
Yeah, basically this one. I think the set where the series converges is measurable, but that is a sequence where these two are equal. So it's equal to the set where the difference between lim-sup and lim-inf equals to 0. That is a random variable, and the set where random variable is 0 is measurable. Yeah. So that's the third part. So should we try 220? If you're not,
yep.
Okay, no matter. I mean, you may like it, you may hate it, but we're going on. So I can't remember which one 220 was. Oh, it's that one. Okay. Yeah. So 220. So F and G are Borel measurable functions. So that means that they are measurable functions with respect to the Borel sigma algebra. And X and Y are independent random variables. And the task is to prove that f of x and g of y are independent. So it's a useful result because it says that if you start with something independent and you start taking functions of both of them, the result is still independent. Okay, so what do we have to do here? Well, to test that something is independent, we have to look at the probability of the set where one random variable is less than alpha and the other random variable, g, is less than beta. The basic definition of independence of random variables says that if the that this should split as the product of the probability of the first part and the second part. And put in an omega here.
Omega or x of omega and y of omega?
Excuse me. Yeah, you're right. Right. So f of x of omega. That's right. And g of omega. That's what it is. Like this. Okay. So what is this? What does it take for f to be in here? I mean, this is the same as f being in the interval from minus infinity to alpha. That is the same as that value being less than alpha. And similarly, this one is the same as being in the interval from minus infinity to beta. But f being in this set is the same as x being in the inverse image of that set. So this is the same as, it's the same set as x of omega being in the inverse image of minus infinity to alpha. Because to be in that set is just the same as if I use f on this one, I end up in this set. And that's exactly what I have here. And this one, in the same way, is the same as being, this should be a y. That y of omega is in the inverse image of the g of minus infinity to beta. But this is a Borel set because f is a Borel measurable function, and that means that the inverse image of these guys is in the Borel sigma algebra. So this is a Borel set, and correspondingly, this is a Borel set. And then we had the theorem that we had to work really hard to prove, saying that if I have two Borel sets, my two Borel sets A and B, then X being in A and Y being in B splits as the probability of X being in A times Y being in B. I mean, we proved that if X and Y are independent, this is the case for all Borel sets. So here we have two Borel sets, so it was split in this way. So I guess that this is a probability that X of omega is in f to the minus 1 interval from minus infinity to alpha times the probability that y of omega is in t minus 1 minus infinity to beta. Like this. And then we just have to unwrap things. I mean, I have to do this backwards, and then I have to find seeing that the first one is the same as f of x being in the interval from minus infinity to alpha. And this one, the second one, is the same as g of y being in the interval from minus infinity to beta. And that's what we wanted to prove. We wanted to go from this one to that one. And we succeeded because, I mean, the problem with the definition, this is the definition of independence, so it only applies to intervals. And since we have f and g here, we leave the realm of intervals and get into inverse images of intervals. But that's quite okay because the inverse images of intervals are Borel sets, and we have proved that this splitting property holds for Borel sets in general.
Can you start the proof by skip the interval and just jumping straight into the
Yeah,
argument?
I could do that. I mean, I could start with a Borel set here, and then I would, down here, I would then have the inverse of a Borel set.
Yeah.
And then I would need to know that the inverse image of a Borel set is a Borel set, but and I'm not sure I know that or not.
Okay.
Yeah. I mean, I know that, but I don't know if the course knows that. I haven't checked it. Yeah. But I mean, in principle, you could do that. It will somehow be smoother, but. Okay, so that's 220. 237 is a rather different kind of problem, but still one that will, I mean, that kind of problem will show up in various guises as we go through the course. So maybe a good idea to take a look at first example. So this is 237. And let me just see that I remember correctly, that it really is this problem that I'm thinking of. Yep, here it is. So x is a discrete random variable taking the integers from 0 and upwards as values. So this is taking values 0, 1, 2, and so on. It's a random variable, and I want to prove that the expectation of x equals a sum, and it's an equal from sum from 1 to infinity of probability that x is strictly larger than n. So this is what we want to do. I mean, there are different ways of doing it. I'm doing it one way. You can also do it at least one other way. But let me keep the one I have here. So let us recall what the expectation is by definition. By definition, E of x is the sum n goes from 1 to infinity n times the probability that x actually has the value n. So that's the definition. So somehow we have to get from here to here. Yeah, as I said, there's at least two ways of doing it, but let me do it the first way that occurred to me, and that is to rewrite this guy here, because we don't want that. I mean, this is going to be the final answer. We don't want inequality in the final answer. We want inequalities of this kind. So can we rewrite that guy as something that has to do with these inequalities? Well, we can do that because the probability that x is exactly n is the probability that x is, now I have to be a little bit careful, that x is larger than n minus 1, I think, minus the probability that x is larger than or equal to n. Did I get that one right? So this is so this is all the guys that is larger than n minus 1, so it may be n plus 1, n plus 2, and so on. And then I subtract this one, which is a probability that you are larger than or equal to n. So the guys that are left here are the guys where you have exactly n. Okay? So let's see if we can make a drawing. So here is a set where x is larger than or equal to n minus 1. Okay. Here is a set where x is larger than or equal to n. That's a smaller set because it's hard to get to be bigger than n than being bigger than n minus 1. And what's in the middle here? So the guys in the middle consists of those that are, something wrong here.
No,
Should be n and n plus 1.
Should be n plus 1 somewhere here,
Yeah.
okay? So this one should be n plus 1, huh?
No, that's n, and the other one is n plus 1.
Yeah, this one is the largest one, this
Yeah,
one is the
yeah.
largest one, yeah. Okay, that looks more familiar. That's good. Yeah. It should be like this. Because, I mean, these are all the guys that are larger than n. These are the guys that are larger than or equal to n plus 1. So the ones that are in between here are those that are exactly. So this is the way it should be. Okay. Glad to see, because this looks much more familiar. So now I split this sum in two pieces. I take the sum n equals 1 to infinity of n of the first guy, p of x being strictly larger than n, and just split this in another sum, n equals 1 to infinity, and if I pull that n in, I get n, and I get the probability of x being larger than n plus 1. Okay. So I want to change these. I mean, here I basically have a sum over all sets of the type x larger than n, and here I also have x larger than something. I mean, I'm just the wrong variable of summation. So I want to change the summation variable in the second one so that I also here have x larger than n. So how do I do that? Well, I'll just let the first one be as it is, n goes from 1 to infinity of n p x larger than or equal to n. And what do I do in the second one? What do I do it down here? Well, I change the order of integration. I mean, if I insist that this should be p of x larger than n, I take all these and multiply this number in front here should be 1 less than this, so this should be n minus 1. So these here are the same pairs as I have over here. I just sort of shifted the index 1 over.
The sum should start at 2, shouldn't it?
Yeah. So the point is that since I started 1 here, I should start at 2 there. It doesn't really match. But in fact, I could start at 0 here because of that n. The 0th term doesn't really contribute. And if I start at 0 here, I can start at 1 here. And then we can combine these two. I'm cheating a little bit here because I'm not thinking about convergence. I could be thinking about convergence, but this means that I should not take sums all the way to infinity, but partly up. So now I can combine these two things. I have n minus 1. So when I combine them, n minus 1 just leaves me with 1. N equals 1 to infinity. Okay. So what I'm really doing here is kind of a discrete partial integration. Because what I'm really doing is that I'm moving if you think of this as a difference, I'm moving that difference to the other side. Here I have the difference between two probabilities. When I go and get over on this side, I get the difference between the two ends. So it's really like shifting a difference, or a differentiation if you want, from one side to another one. So it's an example of what is called obel summation, which is a kind of integration by partial integration for sums rather than integrals. So we return to this later. What is the use? So that was 237, was it? We still have 10 minutes. So do you want 230 or 210?
To 10 maybe?
210?
Yeah.
So, I mean, we've been in this nice abstract realm for a while now, where I'm enjoying myself. Now we're going down to the nitty gritty of actually computing things. So, in 210, we have a situation, if I remember correctly, of 5 girls and 5 boys waiting in line for a rock concert. That's a problem, isn't it? So that is 5 girls, 5 boys. And going through the ticket machine or whatever, and so they have to line up. So they line up in arbitrary order. So they may, for instance, be boy, boy, girl, 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 boy, boy, and so on. But it's completely arbitrary. And we want to look at the position of the first girl. And we want to know the distribution, which in practice means that we want to know what is the probability that she's number 1 in line, what is the probability that she's number 2 in line, and so on. I mean, she cannot be lower than number 6 in line. I mean, that's what happens if all the boys line up first and then leaves the rest of the girl. So she has to be somewhere among the 6 first. So what's the probability that the first girl is number 1? So probability that, let's call this random variable, it's a random variable, the position of the first girl. So what is the probability that the first girl is first in line? Well, it was totally random. There are 5 boys, 5 girls, so it's obviously 1/2. So what's the probability that she's second in line? Well, for her to be second in line, 2 things have to happen. First, the first person has to be a boy, and that is the case with probability 1/2. Now, given that the first person in line is a boy, what is the probability that the second one will be a girl? Now we no longer have 5 boys and 5 girls to choose among because we used a boy already. So there are actually 9 people to choose from. And 5 of these are girls. So we have to multiply by 5/9 there. I mean, since we're not putting the first boy back, you don't get 1/2 or 5/9. Okay, and we can continue in this manner. So the probability that she will be number 3, how would that happen? Well, first of all, the first 2 persons have to be boys. The probability that the first person is a boy is 1/2. What is the probability that the second person is a boy? Well, when we get to the second person, there is a total of 9 people to choose from, 4 of which are boys. So the probability that the second one is a boy is 4/9. So that is the probability that the 2 first ones are boys. And given that the first 2 ones are boys, what is the probability that the third one is a girl? Well, now you use 2 persons, so you have 8 persons to choose from. 5 of these 8 persons are girls. So you have to multiply by 5/8. And then we continue. Is that okay, or do you want me to continue?
No, that's fine.
That's fine?
Mm.
Okay. So the trick is, I mean, I remember, I admit that the first year I did this, I just multiplied by 1/2 everywhere. It's a silly mistake to make, but if you don't have your mind with you, you think that you put the first boy back in the line, but you don't. Yeah. Should we take a look at 232? think I have a little bit of time for that.
If we have time, that would be nice.
Yeah, 2/3, that's the one with fair coins, is it? The fair coin, 4 times? Okay. So I think we can do it here. So that's 230. So fair coin. Everything's wet. Fair coin tossed 4 times. And you want to look at the difference between the number of heads and the number of tails. So x of omega is, let's put it this way, this is the number of heads minus the number of tails. So what are the possibilities here? Well, the possibilities is that you can have 4 to 0, that is 4 heads and no tails. And then of course the value x will be 4. Now you can have 3 heads and 1 tail, and then x will be 3 minus 1, so that is 2. You could have 2 heads and 2 tails, in which case x comes out 0. You could have 1 head and 3 tails, in which case x comes out minus 2, 1 minus 3. And you can have 0 heads and 4 tails, which means that x comes out minus 4. So these are the possibilities. I mean, these are the only values the random variable can have. It cannot have odd values. It can just have the even values between minus 4 and 4. The problem is that these events are not equally probable, so you have to compute the probability for each one of them. So the probability for 0 is just 1 over 2 to the 4, because you have to get heads every time. What is the probability for 3, 1? Well, that is not just one event, because that one tail can happen to come in 4 different places. So there are 4 different chains of events that leads to this one. I mean, each one of them, head, head, tails, head, with their probability 1 over 2 to the 4th. But then the heads can be in 4 different positions. So the probability for this one is 4 times 1 over 2 to the power 4. So then you have the probability for, and by the way, I mean, the other ones down here are symmetrical. So the probability for 1, 3 is 4 times 1 over 2 to the 4. And the probability for 0, 4 must be the same as this one. So 1 over 2 to the power 4. So the only one is left. So the problem is, in how many ways can I arrange for 4 coin tosses, 2 of which are heads? Well, I can do that in 4 over 2 ways. I mean, I can choose the position of 2 tails or 2 heads from 4 in 4 over 2 ways. And each of these will have a probability of 1 over 2 to the power 4. And 4 over 2, 4 times 3, 1 over 2, that's 6, I suppose. So this is 6 times 1 over 2 to the power 4. So here we are. So, I mean, you just need to be a little bit systematic, and then you have to recall your basic combinatorics, whatever you're taking before. Is that okay?
Yeah.
Everybody's happy? Well, everybody's happy because it's over. Okay. See you on Monday.
type 2-spørsmål.
Ja, Maja?
På en 57. Den andre veien er vel bare også å se at du får en, og så får du eller en med T av x lik 1.
Jeg vet ikke når du får noe.